In this example, we're asked to come up with the natural frequencies and modal vectors for this 3-degree of freedom system that is shown. Important to note that we're using absolute coordinates of x1, x2, and x3. Start out by writing down the kinetic energy expressions. 1/2 2m x1 dot squared, 1/2 m x2 dot squared, plus 1/2 m x3 dot squared. So therefore, from this we see that with our generalized coordinates that we have, our mass matrix is diagonal, which is a special form of the symmetric matrix that it always is. The potential, we're going to have the spring on the left is 1/2 k x1 squared. Spring on the top right, it has a stiffness of 2k. The stretch in the spring is given by x3 minus x1 squared. And the spring bottom right is 1/2 k. It stretches x2 minus x1, so that's squared like that. We know that our stiffness matrix is the mixed partials of the strain energy with respect to xi and xj evaluated at the equilibrium state. So K, stiffness matrix, will end up being 4K minus K minus 2K minus K minus 2K K 0, 0, 2K. Of course, as always, K is symmetrical. Therefore, our equation of motion mx double dot plus kx is 0. The solution, constant coefficient linear homogeneous equation, we know that we'll write it down as a separable solution, a synchronous one, where we have this vector x multiplying an exponential, and since m and k are positive definite, we know that the roots will all end up being imaginary. So let's just write that down from the word go. Substituting this in to the equation of motion, we get minus omega squared m plus k, the modal vector x, e I omega t. We know that the exponential can never be a 0. For a non-trivial solution x, this means that we need to have the determinant of minus omega squared m plus k to be a 0. That matrix is a singular. Okay, so what I'm going to do is write out the determinant of that 3 by 3. That's going to be minus 2m omega squared plus 4k minus k minus 2k minus k minus m omega squared plus k, 0, minus 2k, 0, minus m omega squared plus 2k. That determinant is a 0. So as I expand this out, I'm going to write this out as minus 2m omega squared plus 4k times the determinant of the 2 by 2, minus m omega squared plus k, 0, 0, minus m omega squared plus 2k. And then I have a minus k times the determinant of the 2 by 2 of minus k minus 2k, 0 minus m omega squared plus 2k. And finally, the last term in there is going to be a minus 2k times the determinant of minus k minus m omega squared plus k minus 2k in a 0. So all I've done is I've written out the determinant of the 3 by 3 as a set of three determinants combined together. What I will do is simply say that I will expand those. And this gives me the result of minus 2m cubed omega to the 6th plus 10 m squared k omega to the 4th minus 11 mk squared omega squared plus 2k cubed is a 0. So what we have here for the system having 3 degrees of freedom, our characteristic equation is a cubic equation in terms of omega squared. What I'm going to do to help us in solving is I'm going to divide this equation by k cubed. And what I'm going to get is this. I'm going to get a minus 2 m omega squared over k cubed plus 10 m omega squared over k squared minus 11 m omega squared over k plus 2. And the reason for doing this is I'm going to call this parameter mu. This is just a name. So therefore, with that choice, this becomes a mu squared, and this becomes a mu cubed. And the advantage of writing it this way is that the characteristic equation in terms of mu is all in terms of numbers. That is, I can solve this without having to specify a number for m and a number for k, or even a ratio of m over k. Right now, I'm just saying everything is all in numerical form. So this is third order. The unfortunate thing, though, is that there are no easy closed form solution. Which means that we'll need to use a numerical approach. And I'm going to use MATLAB to solve this. In fact, the MATLAB function I'm going to use is called roots. And roots, you just simply need to provide MATLAB with numerical values for these 4 coefficients of the cubic equation, and you get back the answer. And let's remind ourselves that mu here is defined to be m omega squared over k. We'll use that in the end because we don't really want to know mu. We want to know omega, but we'll solve omega or mu first. So the roots that I get are going to be mu1 and mu2 and mu3. Again, I've got these without having to give any values for m and k. Mu1 is 0.2262, 1.2567, that's for mu3, and 1.8754 for mu3. Of course, what we need is omega 1. Omega 1 is going to be the square root of k over m mu1. So that ends up being 0.476 square root of k over m. Omega 2, square root of k over m mu2. And that ends up being 1.21 square root of k over m. And the third natural frequency is the square root of k over m mu3, and that is 1.88 square root of k over m. So these are the three natural frequencies that we need. Now to find the modal vectors. I'm going to write down our three equations. If you go back to the eigenvalue problem, it's really three equations here: minus 2 m omega squared plus 4k times x1 plus the minus k x2 and plus a minus 2k x3. The second equation was minus k times x1 plus a minus m omega squared plus k times x2 is a 0, and then minus 2k x1, and then we have a plus minus m omega squared plus 2k x3. So these are three equations that we need to attempt to solve, or we have at our disposal to solve for x1, x2, and x3. What we see here is equations 2 and 3 involve only two variables, simpler equations than one. So equation 2 tells us that the ratio of x2 over x1 for the jth mode is equal to k divided by k minus m omega j squared. If I divide through by k, again, this becomes 1 minus 1 over 1 minus mu j. And equation 3, again, is just as involving two variables, in this case x3 and x1. So for the jth mode, this becomes the ratio 2k divided by 2k minus m omega j squared. And if I divide through by k, this becomes 2 divided by 2 minus mu j. Equation 1 would give no new information. These are the only two. We can only use 2 out of the 3 equations. So we recall that the best we can do is solve for modal vectors within a constant multiplier. So what I'm going to do is what we've done consistently before, is I'm going to choose the scaling here to make the first position of each vector a 1. So this is going to be true for all 3 modes. As a result, this gives, for our modal vectors, x1 is 1, 1.292, 1.128. The second mode, again, I chose the first position to be a 1, minus 3.895, 2.691, and then the third mode, with the first position being a 1, as with the other two. This becomes a minus 397 and minus 1.318. These mode shapes are shown in the notes, so see figures in lecture book for the motion shapes, response shapes for these three modes. Process here, same as it was for the other examples we've seen. We drive the equation of motion, we set up the characteristic equation, we solve for the modal vectors. The difference here is that we found out for having 3 degrees of freedom, we end up with the third order characteristic equation, which in general we aren't going to be solving in an analytical way. So we need to resort to a numerical means to solving the characteristic equation, and then we back substitute into our algebraic equations to find the modal vectors. As you go up to higher and higher modes, it fully anticipate not even being able to take those problems as far as this. You probably don't want to take a fourth or a 4th degree of freedom, 5 degree of freedom system this far. You likely will want to give MATLAB the matrices themselves and let them solve the characteristic equation and solve the modal vectors directly right from M and K.